Morning. Welcome to Krishna's class. We continue from where we left last lecture. Recall that what we have proved was the following, namely Lipschitz class of functions defined on the bounded interval AB is a proper subset of absolutely continuous functions on the interval AB, which is again a proper subcollection of functions of bounded variation on the closed bounded interval. We are working on compact interval A. So all Lipschitz continuous functions are absolutely continuous. All absolutely continuous functions are functions of bounded variation, but there exist functions of bounded variation which are not absolutely continuous. There exist functions of which are absolutely continuous but not Lipschitz. Okay. So we give an example and in this gap, that means proving that there exists a function which is absolutely continuous but not Lipschitz, we use this example. That's the example that we use. And here, the example that we use is Cantor-Lebesgue. And we will explain this part soon, but need some supporting results on absolutely continuous functions and functions of bounded variation to substantiate it. What we have observed is that functions of bounded variation can be written as the difference of two increasing functions of bounded variation. And absolutely continuous functions can be written as the difference of two monotonically increasing functions which are absolutely continuous. Okay. Therefore, you see that the fact that the functions of bounded variation can be expressed as a difference of two monotonically increasing functions, and all such functions are functions of bounded variation. And absolutely continuous function, if you take an absolutely continuous function on the interval AB, that can also be written as the difference of two monotonically increasing functions. And therefore, the first stage you infer that every absolutely continuous function is a function of bounded variation, because that particular feature, that a function which can be expressed as the difference of two monotonically increasing functions on the interval AB, is a characteristic feature of functions of bounded variation. Okay. Therefore, every function which is absolutely continuous on the interval AB is a function of bounded variation. That is the argument that we give. But at the same time, we shall later see that this cannot be, they cannot be equal. There are some Yes. So the sort of scenario is this. You have then a bigger class which is and a still bigger class this is the sort of Venn diagram that you have for these class of functions. Okay, now these intrusions are non-trivial. That's something. Okay, now let us start working on this idea further. Because I said, made a statement that Cantor-Lebesgue function is the one that is not absolutely continuous, but it's a bounded variation. But before that, we shall prove some properties, or rather, recall some properties of the absolutely continuous function. All these things we have proved earlier. Okay, so this is a result which is a pointer to that. If f belonging to AB is a compact inverse. Compact means closed and bounded. Then f is differentiable almost everywhere, and its derivative f derivative is integrable its derivative is f derivative is integrable, and integral of now the analogous property for functions of bounded variation is, this is the theorem that we have for functions of bounded variation. See, by Jordan's theorem, let me just by Jordan's theorem, f belongs to, in fact it's a characterization, if and only if f is the difference of two increasing functions it is monotonic increasing functions on AB. It's not necessarily strictly increasing, they are just increasing. I mean, they are not non-decreasing. So what I mean to say is that when I say two increasing functions, I mean they are not decreasing on interval. Now this is something that we have, and we know that every increasing function increasing means non-decreasing, is differentiable almost everywhere. Earlier we have seen that for increasing functions, the discontinuities are at most form a countable set. Now here you have much more incisive result. The function is differentiable almost everywhere. Therefore, what we have is this. See, f is equal to f1 minus f2. Both are monotonically increasing functions. This belongs to now you see each one of them is differentiable almost everywhere on the open interval A. And therefore you see that f derivative is differentiable almost everywhere. More or less what you can show is that this f dash is an increasing function. Sorry, an integrable. So this is what you have. So we have the theorem. Or this can be written as a corollary to the above Jordan's lemma or Jordan's theorem. What it says is this, that f belongs to AB, then for implies it is differentiable almost everywhere. Almost everywhere on the open interval AB, and f derivative, that is the derivative of f, is integrable. that is integral is right. So this property is there. It's a consequence of this result, that it is the difference of two what you call, say you have f equal to f1 minus f2. Both are monotonically increasing. Therefore, both of them are differentiable almost everywhere. And then you can actually show that the derivatives are integrable, and therefore you see that eventually the derivative of f is an integrable. That's the proof of that result. Okay. Therefore, what is the consequence of this? Before that, we also look at one example. This example is worth looking at. Slight digression, although very much related. With alpha and beta be non-negative numbers, f is from the compact interval 0, 1 to R. Defined by x to the power alpha sine 1 by x to the power for x belonging to, that means 0 is not included, and at 0 this is equal to 0. Then this the property of this function, when this is a whole class of functions that you have, to give you nice examples. In fact, what happens is this: as beta increases, you see that the oscillation increases. Okay. This function, the sine function, see what happens when beta increases. See, 1 by x power beta is from 1 to infinity. So, if you take any x here, then 1 by x to the power beta is something which increases with beta becoming large. And what happens is, more and more frequently these functions start oscillating. And it is bound by the function x to the power alpha. It's nice to draw for a particular value and get a feeling for this example. It's a very nice example. Now, what is the behavior of this function? First of all, you see that because of the infinite folds that come, see, things become difficult, and the function would eventually fail to be a function of bounded variation. Although, towards when alpha is positive, you see that the function, the oscillation is squeezed between x power alpha. So it's something like this. So this is x power alpha. And then you have, this is the sort of function that because of the modulation of x power alpha, you see that finally you get a series which converges. I mean, earlier we have seen that when alpha equal to 1, then of course you have this function uh, failed to be a function of bounded variation. So in fact, we are making a general statement now. Alpha greater than beta implies f is of bounded variation over the interval now and f dash is integrable this is very easy to prove. Secondly, if alpha is less than or equal to beta, then f does not belong. So this provides you with a whole class of examples and gives more insight into the functions of bounded. Okay. Now, absolutely continuous functions are expressed as the difference of two monotonically increasing functions which are of bounded variation. Therefore, you see that each one of them is differentiable, has a derivative almost everywhere, and you can show that this is also integrable, and they are integrable. But then, for the case of absolutely continuous functions, a much more stronger result is given, and that is what we have, the characterization result for absolutely continuous functions. This is for absolutely continuous functions on the interval AB. F belongs to absolutely continuous on the interval AB. Implies f is differentiable almost everywhere, and its derivative is integrable A to B This is an if and only if theorem. So it's a nice characterization theorem for absolutely continuous functions. Okay. Therefore, this we use to get a function which is of bounded variation but not absolutely continuous. It's an example. Consider the Cantor can refer to Roydel. Search for Cantor-Lebesgue function, and there's a complete discussion on this function earlier, which we have done in our lecture series also. So these are the salient features. Fine. Now, what are the properties? First of all, phi is continuous on it is these type of magnificent functions which create mathematics, in the sense that the distinction between the functions of bounded variation and the absolute continuous functions, and then leading to nice characterization theorems, and the gap between functions of bounded variation and the functions of absolutely continuous functions is highlighted by this example. So you look at this function. What is this function? This actually is 0 at 0, and at 1 it is 0. So you have phi 0 equal to 0, equal to 1. The second aspect is that phi is a continuous function. Second aspect is that phi is monotonically increasing function, by which I mean it is non-decreasing. Increasing function. The third property is that phi derivative x is almost everywhere, and this is equal to 0 almost everywhere. On 0, and phi derivative almost everywhere on 0, 1, that is on the complement of the Cantor set. Now we know that the Cantor set is not countable. Not countable. Although its measure is 0. Therefore, it is on the complement of a measure set phi dash equal to 0. Okay, that is f dash equal to 0 almost everywhere. On what is the consequence of that? We get 0 equal to integral f derivative, and that, of course, is equal to, see, if f were an absolutely continuous function, you would have got this result. f0. But what is this? Is 1, this is. Therefore, you see that this is in fact not equal to one, which is equal to f. Therefore, you see, this is because f1 is 1, f0 is 0, therefore this is equal to 1. So you have integral 0 to 1 f derivative is not equal to, which implies, because this is a characterization theorem for absolutely continuous functions. Okay, this is a characterization theorem for absolutely continuous functions. Therefore, f does not belong to however it is of bounded variation, because the total variation is equal to 1. Because it's a monotonically increasing function going from 0 to 1. Okay, so it's a function of bounded variation. That is the Cantor-Lebesgue function. So these inclusions are proper. So the first inclusion is not of much significance though for our analysis, but we see that this is AC in both these cases f derivative exists almost everywhere. So f derivative exists almost everywhere. But in this case, what you have is, okay, f derivative is integrable. Now this is true for both the cases. But the problem that you have is this. Integral f derivative in this case is and this is a characteristic feature. Whereas here, if f does not belong to AC, this is this property that we have used to show that the Cantor-Lebesgue function has this property, which is it's a BV function, but not an absolutely continuous function. So f the Cantor-Lebesgue a function of bounded variation but not absolutely continuous. So this is the first set. So this is a proper container. Now, when do you say a function is the indefinite integral, right? Integrable function. So we'll make a definition and then later give the nice version of the fundamental theorem of calculus operation. We define the following function. A function on closed bounded interval AB is the indefinite integral of G over provided G is Lebesgue integrable and so this is the function. We write that's the definition. Now we observe the following. The immediate theorem, if f is absolutely continuous AB, if and only if it is the indefinite integral of an indefinite integral so a function which is an indefinite integral over AB is an absolutely continuous function. Okay, so what you generate out of this, take an integral, take the indefinite integral of that, add to that a number that is fa, then this function is certainly an absolutely continuous function as long as G is an integral. That's a characteristic. Now we will just indicate what happens. Now you see that if f is absolutely continuous, then it is absolutely continuous on Ax AB. Therefore, what we have, which implies we have got the characterization in terms of this integral a to x, integral a to x f derivative, which exists almost everywhere, is equal to fa, that is fx equal to integrable function. So it takes the place of g, and you see that f can be written as in this particular. Therefore, yeah, this can be written in this particular. So one side of the theorem, that is, if f is absolutely continuous on G, then it is an indefinite integral over. Okay, the converse can be proved, and so this is the forward equation. The converse, I am not giving the proof. The converse is if this is a function, you need some craft. F is now fx equal to some g. Then one can prove that and this needs some work. Okay, so I have given the proof earlier, so I am not going to. Whenever it is follows immediately, it comes, I will just give it. Okay. So we have used this fact, that this characterization theorem, and we have concluded that the Cantor-Lebesgue function is not an absolutely continuous function, but is a function of bounded variation. Now we have the following theorem. Let f be a monotone function then f is absolutely continuous if and only if integral a to b f dash that's a characterization of such functions for monotone functions, and later you have monotone f is absolutely continuous. It can be written as the difference of two monotone functions. If both these monotone functions are absolutely continuous, then this property would follow, and consequently you have this. So you have, and one of the immediate consequences of this is that the following. Now define one of the theorems that you can immediately prove is this. Let simple consequence of this. And what it says is this. Suppose we define f of x equal to defined as integral a to x dt. Then what this theorem says is that f derivative of x if is differentiable and f derivative of x exists almost everywhere, and this is equal to f of x. Now this is the fundamental theorem of calculus. Okay, there are two pieces for it. One on the integral of that. So if f is an absolutely continuous function, then it is differentiable almost everywhere. Okay, and the derivative is integrable, and you have this result, that is integral a to b f derivative equal to this result is satisfied, and this is one part of this whole problem. The second part is this one. If fx is equal to integral ft dt, where f is an integrable function, then f derivative of x is equal to f of x almost. So you see that for all absolutely continuous functions on the interval ab, you have the fundamental theorem of calculus holding good. So we infer. So this is our conclusion. That's the best part of it. So absolute continuity essentially characterizes functions for which the fundamental theorem of calculus. Okay, so that's the inference. Let me just show. So, okay. So we shall conclude this way. F is absolutely continuous on AB. Then the fundamental theorem of calculus. Holds good for and of course needless to say that calculus holds therefore this gives you a nice characterization of the class of functions and I mean under the new regime of Lebesgue integration, absolutely continuous functions on compact intervals are those for which the fundamental theorem of calculus holds and vice versa. Okay. So thank you very much, and that concludes that part. So I stop here today, and then the next lecture would be working on our final question, namely, do you have completeness property taken care of under the new integral, that is Lebesgue integration. So all our purpose was this. RAB was not to construct the analogous class which you call LAB. Is that? Then we can go even further and show that LPAB is. So thank you very much. With that we conclude the review of the Lebesgue integration theory, and then we will take off to consider the concept of general. Thank you.